Good morning, ladies and gentlemen. It's Elwood Chepansky, and we're doing workshop physics again. Last time I spent 14 minutes doing a lesson on transformers. And that was a difficult lesson, and we started getting into ideas that are more abstract and maybe not so easy to understand with simple words. Remember, physics is the same for elementary students as it is for college students. We all start at the same place. The ideas become a little bit more sophisticated, and sometimes when we introduce the mathematics, then life actually becomes a bit more difficult. But understanding the ideas and the concepts and the way things work is what we're after today. So I'd like to extend a little bit on my discussion of transformers and actually show some very fascinating demonstrations that are very useful. I'm not going to teach so much about the physics, but I want to give you demonstrations of how we use these ideas, okay? And I will also introduce maybe a couple of new terms, but I won't spend a lot of time explaining them. Okay, so here we go. Now, last time I explained that this coil of wire wrapped around this bolt was an electromagnet. The current flowing through the wire creates a magnetic field. We make the windings in a coil so that the magnetic field is enhanced or enlarged, and the magnetic field of the coil magnetizes the iron, and so there's a north pole and a south pole on the iron, and we have an electromagnet. Now, that's a wonderful idea, and what I want to do now is place another small magnet near the end of this electromagnet, and I'm going to tap the voltage of the battery terminals so that a current will flow through the coil and will magnetize the iron rod. And I want you to notice that this little magnet here is going to move. That is, the magnetic field from this electromagnet is going to attract or move or cause, it could repel, but it's going to cause it to move. Now, notice that this is just about 2 feet of wire, so it's a short circuit. We talked about short circuits earlier. We burned up wire. So when I tap this, it's a short circuit, but the amazing thing about this is this coil of wire, actually, when it creates the magnetic field, it also creates a voltage that will oppose the current that I'm applying. And that's what I want to illustrate today. Anytime we have a current, we have a magnetic field. Anytime the magnetic field is changing or building up, it's creating its own magnetic field, which is going to oppose the cause which is producing it. So my light is flickering. So now I'm going to create a magnetic field in the coil. The coil is going to oppose the current that I'm trying to put in here. And that's a wonderful thing. That process of opposing what I'm doing in the case of a coil is called impedance. It's not resistance, but the current doesn't build up nearly as fast as if it was a straight wire. It's impedance, and that means that while the magnetic field is building up here, it's creating a voltage which opposes the cause which is producing it. Okay, watch the magnet. Well, it happened the first time. The magnetic field, due to my electromagnet, immediately causes a magnetic field which attracts the field of this magnet here, and they come together. The point that I'm trying to make now, though, is not that this is an electromagnet. The point I'm trying to make is when I cause the current to flow in this coil, the coil reacts by trying to stop the current. It opposes the current. So there's a law that states that, basically it's Lenz's law. It says the voltage which is induced will be in such a direction so as to oppose the cause producing it. The cause is a current flowing, and the magnetic, it's called magnetic induction, the voltage created will try to oppose that. Okay, that's a fabulous example, but there's a better example that I think is quite amazing. And these are two copper pipes. This is a steel pipe, and this is a plastic pipe. If I drop a magnet down a steel pipe, I can't do it. It just sticks because the iron, or the steel is made out of iron, and iron becomes magnetized and nothing happens. However, if I drop the magnet down a copper pipe, it falls according to the force of gravity that is on it. Here's what is fascinating. If I take a copper pipe, which has electrons that are free to move, it's not an insulator like plastic is. If I drop this magnet down the copper pipe, it'll take a long time to fall because the moving magnetic field causes a current to flow in the copper. The current that flows in the copper creates a magnetic field that is opposing this one. That is, the falling magnet causes a current, and the current causes a magnetic field that opposes the cause producing it. The cause producing it is gravity is pulling down. So the magnetic field is going to push back up. Here we go. We're going to drop it in, and I can wait a long time before it gets down here to the bottom. If you don't believe me, here's a piece of wood that's not magnetic, and I can barely get down there in time to catch it. In fact, we can have a race between a piece of wood and a magnet, and I'm going to put the piece of wood in the long pipe here, and I'll put the magnet in the short one and drop them at the same time, and notice that the wood will travel much faster because there's no magnetic interaction. Okay, huge difference in time, because the wood is not experiencing a force to retard its motion, but the magnet is. There it is. Beautiful example of Lenz's law. Okay, finally, to end this, I want to talk about where that is, again, important. In the old days meaning when I was a kid, the tractors and Model Ts, by the way, I'm not that old, but they still existed. Well, the tractors and Model Ts had a battery, but they didn't have the modern ignition system. So what they had were called ignition coils. Ignition coils, and these coils could be connected to the battery, and a high voltage would be generated, which would spark the spark plugs. You never see these anymore. This is old stuff. I've saved these for over 60 years because I find them so interesting. I have 4 of them out of a car, and I took one apart hoping that I would be able to show you the coils inside, but they fill the entire system with some insulating material, so I can't do that. But inside here is a transformer. It's a set of coils. However, the primary has a few windings and the secondary has thousands of windings. So the voltage that comes out of this when we connect a battery to it, the voltage that comes out is huge, and it's large enough to create sparks. Okay, I want to illustrate that over here. Remember, excuse me. Remember, when we touched this here, there was a voltage which was generated to oppose the cause producing it. Well, here I have one of the coils set up so that it will be attached to this battery, and when I close the switch here, then I'm allowing current to flow to the coil, but we're getting this huge voltage, and it's not AC. Here is a battery which creates direct current, and yet we're getting the effect of a transformer. Well, this is what's important. anytime the current is changing in any coil, it's opposing the cause which is producing it. Anytime I touch this, there's an opposition. When I touch it, it's an opposition in this direction. When I take the connection away, it again wants to oppose it. Now there was a current flowing, now the coil wants to stop the current from flowing, so it generates a voltage in the opposite direction. The effect is the coil is always impeding the current that we are applying. Well, how can we make the voltage change when we only have a DC battery? What we can do is stop and start the current flowing in the coil very rapidly. And the designers of these coils did it in such a way that there is a magnetic switch right here. Actually, the bottom of this is a little magnet, so when the current flows, there's a little switch that moves back and forth, opening and closing the circuit, and that means that the voltage on the primary coil inside here is stopping and starting, stopping and starting, stopping and starting. And even though it's not AC like this, it starts and stops and starts and stops. And each time it starts and stops, it generates a voltage. And if that starting and stopping is in the primary, then the voltage, the high voltage, will be generated in the secondary. So here we go. Here is a coil from a Model T or a Fordson tractor from 80 years ago. And if I close the circuit here, notice I have a very high voltage generated between these two wires, a voltage high enough to make the electrons jump across this gap. But also notice on the back side here, I'm getting some sparking because this is where the switch is opening and closing very, very rapidly. We can actually tune the switch with this little knob. So it's stopping and starting the current in the primary coil so rapidly that each time it stops or starts, it generates a voltage spike, and that voltage spike occurs here as a spark across this gap. Let me see how big we can make the gap. Yeah, that's more exciting. Let's make it bigger. Nope, too much. Okay, what's significant about this? Well, a lot of significant and fun ideas, but what we now know is that we can convert DC to AC, but it's not a nice smooth sine wave. It's a pulsed AC, but it's still very useful for generating these high voltages. Okay, that's the end of the lesson for today, or that's the end of the discussion for today. I hope you enjoyed it. I'm going to take a little break now and do a few other things, but we'll continue thinking about physics ideas and presenting them when we can.